Well, hello, good evening, and welcome to today's live interaction session. So, presently we are in week 12 of this NPTEL session, um, and this will be the last session for this particular course. And so with that small introduction, I'm going to turn off my video and we are going to start today's session. So again, I would like to welcome you all to this live session. So, uh, welcome to the NPTEL course, Advanced Reinforced Concrete Design, and the course instructor is Professor Surya Prakash from IIT Hyderabad. And today we are going to conduct the live session for week 12, and the session is presented by me. My name is S. Lalit Sagar. I'm a doctoral candidate and PMR fellow in the Department of Civil and Environmental Engineering at IIT Delhi. So, as we have been doing for all these, today is the 12th and the final week. So, as in every class, the agenda for today's session is that we're going to be solving some sample problems on the following topics. So, in week 12, we covered the module 10, that is pertaining to the analysis and design of two-way slabs. So, in module 10.1, we looked into the overview of the reinforced concrete slabs, particularly what are the different types of slabs and the moment distribution and the deflection profile of the one-way and two-way slabs, and what is the effect of torsion in two-way slabs. And we also looked into the chord coefficient method that is prescribed by the IS 456 for the design of one-way and two-way slabs. We also solved one numerical problem. And in module 10.2, we looked at the direct design method and what are the factors to be checked for using the direct design methods. So, direct design method, in order to apply that, there are certain conditions which the slabs have to qualify. So, we looked into those conditions which are necessary for us to analyze and design a slab as per the direct design method. Then we looked into the steps involved in the direct design method. That is the determination of the static moment and determination of the distribution of the moments in the longitudinal and transverse direction and so on. And then we also solved one numerical problem on the uh, design of RC slab using the direct design method. And finally, we looked into the equivalent frame method and how it is different when compared to the direct design method. Uh, so, in order to apply the direct design method, there are certain limitations that uh, the slabs have to qualify certain criteria. But on the other hand, the equivalent frame method is more versatile. It can be adopted to slabs having different geometric profiles and different loading conditions. So we looked into the basics of the equivalent frame method, and then we explained what is an equivalent column and its significance in the EFM. And finally, we also carried out one design problem, analysis and design problem. So as we have always been discussing in this particular course, the analysis and design go hand in hand in the design of reinforced concrete structures. So we looked into the analysis and the design of two-way slabs as per the equivalent frame method. So, with that, introduction, we can proceed to the questions for today's session. So, let us start with the question one, right? So, right. So, identify the incorrect statements on the dimensions, behavior, and design of reinforced concrete slabs. So, there are five statements which are provided over here, and we need to identify the incorrect statements among the five statements. Okay. So I'm going to take a pause and let you read the options. Then we can look at the incorrect statements. Yeah, so we have five statements over here. So I'm going to read them one by one. When the ratio of L by S is equal to or greater than 2.0, it is called a two-way slab, where L is the longest span and S is the shortest span. Okay. And the second statement is one-way slab deflect primarily along the longest span. Statement C is in two-way slabs, bending will take place along two horizontal directions like a dish-like form. Statement D is in one-way slabs, main reinforcement is required along the longest span. Statement E is in two-way slabs, steel reinforcement is designed along both the horizontal directions. So the incorrect statements in this particular question are options A, B, and D. Okay. So when the ratio of L by S is equal to or greater than 2, then it is called a one-way slab. So statement 1 is incorrect, and the one-way slabs deflect primarily along the shortest span. So statement B is also incorrect. Statement C is correct because two-way slabs tend to deflect in a dish-like form along both the horizontal directions. Statement D, in one-way slab, main reinforcement is required along the shortest span because it bends along the shortest span, so it requires the reinforcement also to be provided in the shorter direction. So statement D is incorrect, but statement E is correct because in two-way slab, steel reinforcement has to be provided along both the horizontal directions. Okay, let's move on to the second question. Yeah, so in second question, we are having this numerical problem, right? So, so this is a big problem that is divided into small components. So we can say that the different steps in the analysis of these two-way slabs has been converted into problems of uh, problems of a few number of limited number of steps. Okay, so let us see what is the question. In the floor slab system of a multi-story building shown in the figure below, the slabs are supported by 230 thick masonry walls. Okay, so the slabs that is divided into 9 panels is supported by 230 thick masonry walls. Assuming the floor finish of 1.5 kPa and live load of 5 kPa, in addition to the self weight, determine the factored moment along the shortest span of the interior panel S4. Okay, so we need to focus on the interior panel S4 and we need to determine the factored moment along the shortest span. So out of the two horizontal directions, which is the shortest span? So obviously it is evident from the diagram that this particular direction, that is the vertical direction, is the shortest span. Okay, so let us proceed to find out the factored moments of the interior panel along the shortest span. So it is given that the slab thickness is 150 mm. So the slab thickness is 150 mm and the clear cover is 20 mm and the steel rebar is having a diameter of 10 mm. Okay, let us proceed to solve this problem now. Let me draw a small sketch. Okay, let me take the pen. So this panel S4 is the focus. It is having a length of 5 meter in the horizontal direction and 4 meter in the vertical direction. Let me draw a small sketch, for reference sake. So since it is an interior panel, we need to show the discontinuity along all the 4 directions. So this is the symbol for discontinuity, or yeah, you can say that it is continuous. So we are showing this symbol, and this center to center distance would be, uh, I believe that the interior span is 4,000. So the center to center would be, okay. Let me mark the center line so that uh, we are clear as to what we are. So as always, we are going to start. We are going to solve the first problem, quite slowly, looking at all the data and how to take them into consideration. Then we can actually proceed to accelerate and solve the remaining questions. Right? Right? So, let me write that the shortest span, that is Lx. Okay. It is the smaller of first the center to center distance between the supports, that is 4230. or it can be the center to center, sorry, the clear span plus the effective depth. L clear plus effective depth. Okay, so how do we determine the effective depth now? Okay, so it is given that 150 mm thick, 20 mm cover, and steel rebar of 29 mm diameter. Okay, so let us calculate the effective depths over here. Okay, dx is equal to 150 minus 20 minus 10 by 2, right? That is 125 millimeter. And dy is 125 minus 10, that is 115 millimeter. Okay, so going by this, the values of dx and dy, we can say that this is equal to 4000 plus 125, that is 4.125 meter. Okay, and then what is the longest span? Let me write it here. Longest span, that is Ly, is the least of the center to center distance is 5230 millimeter. And secondly, let's use this equation, that is 5000 plus 115, that is 5.115 meter. So this is the actual, let me take another color. So we have to pick the smallest value of these two values. So this would be Ly and this would be Lx. So we need to determine the value of Ly by Lx. Okay, that is going to govern the moment coefficients. Okay, so let us find out the value of Ly by Lx. Ly by Lx is equal to 5.115 divided by 4.125, which gives us a value of 1.24. Having found out that value, let us proceed to uh, determine the moments around the shortest span. Right, we have here mx positive is equal to alpha x positive into wu into lx square. Okay, and we have this mx negative is equal to alpha x negative into wu into lx square. Okay, we have these equations over here. So we need to determine the value of wu first. So wu is the factored distributed load that is given by, let us take the factor of 1.5 outside. Okay, and first we're going to take the self weight of concrete, that would be 0.15, that is the thickness of the slab, multiplied by 25 kilonewton per meter, plus what about the finished load is 1.5, live load is 5 kPa. Let us plug those values, 1.5 plus 5. So when we solve that, we get the value of Wu as 15.375 kPa. 15.375 375 kPa. Okay. And how do we find out the value of Lx plus and Lx minus? We have the value of Ly by Lx as 1.24, right? Let me write it down over here. I'll take a different color. So, yeah, Ly by Lx is equal to 1.24. Okay. So, alpha x positive and alpha x negative. So, for the interior panel, first we need to find out the value of alpha x, right? Um, for 1.24, we have by the linear interpolation, we find out that the value of the positive moment coefficient has to be between 0.032 and 0.036. That turns out to be 0.0336. Okay, 0.0 double sorry double 3 6. And what would be the value of alpha x negative? That has to be interpolated between 0.047 and 0.051. That turns out to be 0. Oh, I'm sorry, it has to be between 0.043 and 0.047. That turns out to be 0.0446. Okay, so let us plug these values in the equation that is mentioned above. Okay, that is 0.0336 into 15.375 multiplied by what is the value of Lx, that is 4.125. Okay? 4.125. Similarly, this mx negative would be 0.0446 into 15.375 multiplied by 4.125. Okay, I'll take a different color and write down the final answers. So the final answer of mx positive would be 8.8 kilonewton meter. Okay, 8.8 kilonewton meter. And the value of mx negative would be 11.7 kilonewton meter. 11.7 kilonewton meter. Let us go back and see which option matches. Yeah, 8.8 and 11.7. So option C is the correct response. Okay. Now let us proceed to the next part of the question. That is question 3. For the floor slab system that was mentioned in question 2, determine the factored moment along the longer span of the interior panel. So previously we did the exercise to find out the moment along the shorter span, right? Moment along the shorter span. Now we need to determine the moment along the longer span. Okay. So what would be the equation for that? It is similar to, the equation that we determined earlier. Okay. So my is given by alpha y w into lx square. This is wu in fact. And for the positive and negative moment, it can be written simply as alpha x positive and alpha x negative. Okay, let us start solving the problem now. So, and we know that the value of Ly by Lx is 1.24. That will come up later in the solution, right? So we have My positive is equal to alpha y positive into Wu into Lx square. So please note that irrespective of determining the moments along the shorter span or the longer span, we are always considering the value of the shorter span length, that is Lx. Okay, and we have this My negative. My negative is equal to alpha y negative into Wu into Lx square. Okay, let me separate this equation over here, and we know the value of Wu as how much? 15.375. 15.375 kPa. Further, for the value of Ly by Lx is equal to 1.24, we have the value of, uh, sorry, this has to be alpha y positive and alpha y negative. So it doesn't really require the interpolation because we have the value straight away over here. Alpha y negative is 0.032 and alpha y positive is 0.024. Okay, 0.024. Here we have 0.032. So let us plug these values and find out the value of the moments, final moments. So 0.024 into 15.375 into 4.125. My negative is 0.032 into 15.375 into 4.125. Now let us calculate this and find out the final answer. So this would be 6.3 kilonewton meter. So I request all of you to just verify this. So verify the calculation and see to it that you're getting the same answer. And my negative would be 8.4 kilonewton meter. And of course, it's going to be negative. Okay. So let us look at the options now. Yeah, so option D is the correct response. Okay, let us proceed to the next question now. So the question 4 is, it's a conceptual question which tests the understanding of our theory of the direct design method. So identify the correct statements with respect to the direct design method of two-way slabs. Okay, so select all the correct options. Okay, I'm going to take a pause and let you to read the options, then we can look at the correct statements. So let us look at the correct answer now. So the correct answer is, the correct statements are options A and C. Okay. So statement A states that the direct design method is an empirical method of distributing the moment between the slab and the beam sections. So option A is correct. Okay, because it is an empirical method where the moment between the slab and the beam are distributed. So the statement B is incorrect because the direct design method tries to simultaneously fulfill the criteria for the limit state of collapse as well as the limit state of serviceability. Okay, so option B is incorrect and option C is correct because direct design method involves the single cycle moment distribution for the analysis of structures. Okay, it does not include various iterations as we do in the equivalent frame method. And option D is incorrect because the direct design method does not give the accurate results when we are dealing with asymmetric dimensions and the loading patterns. Okay? So one of the criteria to use the direct design method for the analysis and design of slabs is that it needs to the slab panels need to have symmetric dimensions as well as symmetric loading patterns. Okay, so statements A and C are correct in this particular question. So here you can look into mm, the slide that was covered in this week's lecture. Okay, so we'll proceed to the next question, which is, we are going to be going into the direct design method. Okay, so the plan of a two-way floor slab system, okay, along with the beam and column lines are shown in the figure below. Okay, the floor to floor height is 3.5 meter. The columns are having a dimension of, so the columns are having the dimensions of 400 by 400 millimeter, and the beams are 400 by 550. Okay, that is 400 width and 550 depth. Determine the beam stiffness alpha B for the beam along the edge A2 and A3. Okay, so we need to determine the beam stiffness parameter alpha B for the beam that is highlighted along the edge A2 A3. Okay, it is adjoining the exterior panel S1, and we need to determine the beam stiffness parameter alpha B, and we need to consider the slab thickness as 180 mm. Okay, so let us proceed to solve this problem, right? So first we need to draw a sketch of the cross section, right? We need to consider beam along the uh, edge A2 A3. Okay, so it is like we're going to cut this, cut provide a cut to the section along here, along this dotted line, right? And this is what the beam would look like. Okay, so let us remember that it's a beam that is supporting an exterior panel. Okay, okay, so we have seen that the width is 400 millimeter for the beam and the overall depth is 550, right? So let me write down the width over here. The overall depth is 550, right? And we know that the slab thickness is 180 mm, right? So what would be the depth of the web over here? That would be 370 mm. Okay, so now what would be the width of the flange that needs to be considered for the analysis? Okay, that is very important. In fact, I could not include the slide from the lecture slides. Okay, I could not insert the picture from the lecture slide, but I suggest you to look at the formula that is considered to determine the width of the beam flange. So the formula is BW plus DW. Okay, BW plus DW. So this is nothing but the width of this flange is equal to the width of the web plus the depth of the web. Okay, so that turns out to be 770 mm. Okay, so once we have done that, we need to locate the neutral axis depth. Okay, so let me take a different color. Okay, and I'm going to draw a section passing through the web of this cross section. Okay, this is the neutral axis, right? So what is the formula to determine the neutral axis depth? location of neutral axis. So let us call it as x bar is equal to summation of a into x bar divided by summation of a. Okay, that we can divide this section into two rectangles, right? Okay, so let us take the moment of the area about this top fiber. Okay, so that would be 770 by 180, 770 by 180 multiplied by 90 plus 400 by 370 multiplied by 180 plus 370 divided by 2. And we need to divide the whole thing divided by the area, that is 770 by 180, excuse me for that, plus 400 by 370. So what is the value of x bar that we find out? X bar is equal to 232 millimeter. Okay, so our assumption is indeed correct. The neutral axis lies below this junction of the flange and the web. Okay, so yeah, let me just make a mark and write down the distances from the extreme fiber to the neutral axis depth. Okay, so this would be 232, and this particular distance would be how much? 550 minus 232, that is 318. Okay, so now we need to determine the uh, moment of inertia of the beam section. Okay, I'll take a different color now. Let me take green for better contrast. So this moment of inertia of the beam section is determined using the parallel axis theorem, that is IB is equal to IXX plus AH square. That is, we need to determine the moment of inertia about the centroidal axis plus the area multiplied by um, the lever arm square. That is, the lever arm is equal to the centroidal axis of the section considered and the layer about which we are determining the moment of inertia. That is, in this case, it is the neutral axis. Okay, so let me write down the values and simplify this. Is equal to, so let us calculate this flange section first. That is 770 by 180 cube divided by 12 plus two 32 minus 90 square. So if there is any doubt, please feel free to reach us out. So what we're doing is we are going to determine the moment of inertia of this section, this flange section, and this h is equal to the distance between this neutral axis and the centroid of this layer. Okay, and then let us now consider the web section. So that is 400 by 370 cube divided by 12 plus 400 by 370 multiplied by 318 318, okay, minus 370 by 2 or 185 square. So upon simplifying this, we get the value of IB as excuse me, The value of IB is 7475.36, 7475.36 into 10 to the power 6 millimeter power 4. Okay. Having found out that, let us proceed to find out the value of IS, that is moment of inertia of the slab section. Okay. So how do we find out the moment of inertia of the slab section? So first of all, we need to consider this only half of the span. So that is 3000 mm, and then you add the half of the width of the beam. Okay. So essentially what we are doing over here for the slab section is that, let us consider that this is being supported over the beam. Okay. This is the slab. This would be the center line, right? So from here to the center line, it is going to be 3000 mm, and then another half width of the beam, total width, that will give us a value of 3200 mm. Okay, and the thickness of the slab is 180, right? So IS would be 3200 by 180 cube divided by 12. Okay, that gives us a value of 155.2 into 10 to the power 6 mm power 4. Okay, so what would be the value of alpha b? Alpha b is equal to I IB by IS. Okay, so when we substitute the values of IB and IS, we get the value of alpha b as 4.8. Okay, I request you all to verify this value that we are getting. So option A is the correct response. Okay, now let us proceed to the next question, right? So for the two-way slab, for the two-way slab panel system given in question 5, determine the beam stiffness parameter alpha b for beams along the edges A2, B2 and A3, B3. Okay, so A2, B2, this is A2, B2 and this is A3, B3. We need to determine the slab stiffness parameter. Okay, so what we are doing essentially here is that first we are going to we are going to determine the beam stiffness. Okay, beam stiffness of all the uh, beams which are supporting this slab panel S1. Then we are going to determine the thickness of the slab in order to limit the deflection as per the Canadian code. Okay, that is the actual objective of our the problem, and we are just approaching that through this small steps or small questions. Okay, so the procedure is same. We need to consider a section across this beam, right? So what does that section look like? Okay, so it is having a width of 400 mm as usual, but on the unlike the previous one, so this is it is continuous along. It is the beam is supporting slabs along both the directions. Okay, so it's going to be a T section, right? Okay, so it is going to look like this. So A2 H A2 B2. Okay, let me write here H A2 B2. Okay, this is what we're looking at. Okay. What is the width over here? This is 400 millimeter. Okay, and what would be the thickness of the slab? That is 180. And what would be the depth of the web? That is 370, right? Because we know that the overall depth of the beam is 550 millimeter. So now, what would be the width of this flange section, right? So the equation is BW plus 2DW is, it should be less than or equal to BW plus 8DF. Okay, so this turns out to be 400 plus 2 times 370. That is 1140. Okay, 1140. Okay, and if we consider this BW plus 8DF, so the value is significantly higher when compared to this one. Okay, so we are going to keep this value. Okay, so okay, so here the value is 1140. So again, the procedure is same. We need to locate the depth of the neutral axis. Okay, let me draw another. Okay, let us assume that the neutral axis lies in the web section. Okay, we're going to be filling out these values later on. Okay, now x bar is equal to a into x bar summation, right, divided by sum of a. Okay, let us solve that. 1140 by 180 into 90 plus 400 by 370 into 180 plus 370 by 2 divided by the area, right? That is 1140 by 180 plus 400 by 370. Okay, so the value of x bar in this case is how much? 205.23 mm. 205.23 mm. Okay, so the value of uh, this distance is given by 205.2. Okay, I'm going to leave it at the first decimal place, and this value would be 550 minus 205.2, that is 344.8. 344.8. Okay, so let us proceed to find out the value of IB, or the moment of inertia of the beam section, right? Okay, like that. So IB is equal to, again it is determined based on the parallel axis theorem, that is 1140 by 180 cube divided by 12 plus 1140 by 180 into 205.2 minus 90 square, right, plus 400 by 370 cube divided by 12 plus 400 by 370 into 344.8 minus 185 square. Okay, so the value of IB turns out to be how much? 8745.8745 to 10 to the power 6 power 4. Okay, and now what would be the value of IS? IS is what would be the width initially? So width is, we are having this half of this width. Okay, that is half of 750 7.5 meter, 7.00 divided by 2. Okay, plus 200, that is 3950. Okay, okay. Excuse me. Okay, I would like to, correct the mistake that I did. So we need to consider the entire width of the slab, because earlier we were considering the beam that is supporting half of the slab panel. But in this case, this particular beam, that is A2, B2, it is supporting the slab on both the directions. Okay, this particular beam is supporting the slab on both the directions. So we need to consider the entire span width, that is 7500. Okay, so let me draw a small sketch, so that we are clear as to what are the dimensions that we are dealing with. Okay, let us consider that this is the beam and this would be the slab. Okay, apologies for the the miniature diagram. I hope that you'll be able to understand and use it in our problem. So the width is 7500 and the depth is as usual 180 mm. Okay, so the IS value would be 7500 by 180 cube divided by 12. So the value of IS would be how much? 3645 into 10 to the power 6 power 4. So we have the value of alpha B for the edge A2 B2. Okay, alpha B would be IB by IS. So that gives me a value of how much? 2.4. So the value of alpha B for the beam A2 B2 is 2.4. Okay, so option C is the correct response. So let's proceed to the next part of the question. So first we determine the alpha B for this particular edge, then we determine for this particular edge. Okay, 2 and 3. Okay, because this is same for both these edges. Now we need to determine the alpha B for the edge B2 B3. Then we are going to determine the depth of the slab in order to fulfill the deflection criteria as per the Canadian code. Okay, so let us proceed with this problem now. Right, let me draw the um, sketch of the cross section first. Right, so we have the beam. Okay, then we have the web, and then we have the flange over here. Right, and the width is 400 mm, right? And the overall depth is 550 mm, right? And then the depth of the slab is 180, okay? And the depth of the web is 370 mm, right? 370 mm. And we have looked the formula for the width of the flange, that is BW plus 2DW, that is 1140 mm. 1140 mm. Okay, so this is about the beam section. Let me draw the the section of the slab section also over here. Let me draw the slab section so that we can proceed to find out the value of IS. Okay, so what is the depth or the thickness? Rather, thickness is 180 mm, and the center to center distance of the slab that is supported by the beam for this edge B2 C2, sorry, B2 B3, that is 6 meter. Okay, so that is 6,000. So for a change, let us find out the value of IS first. IS is how much? 6,000 by 180 cube divided by 12. So that gives us a value of 2916 into 10 to the power 6 mm power 4. Okay, and the usual drill is same for this T section. Okay, let us just proceed to find out the value. So in fact, the beam section is exactly the one that we solved in the question 6, right? So the value of x, in this case, or x bar rather, would be the same as that we found out in the previous. So the dimensions of the beam are exactly the same as in this question. So it is 205.23. X bar is 205.23 mm. 23 mm. Okay. So IB, it is same as the previous question, right? So yeah, it is 8745 into 10 to the power 6. 8745 into 10 to the power 6 mm power 4. Okay. Now we know that the value of alpha b is equal to IB by IS. Okay, that is 8745 into 10 to the power 6 divided by 2916 into 10 to the power 6. That gives us a value of how much? 3.0. So the value of alpha b for the edge B2 B3 is 3.0. So option C is the correct answer. Okay. So let us see what to do with all the beam stiffness parameters that we have determined for all the beams supporting the panel S1. Okay, so determine the there is one more one more parameter that we need to determine now. So determine the moment of inertia of the beam slab member. Okay, so we need to determine the moment of inertia of the beam slab member. So let us remember that this is the shortest section. So sorry, this is the shortest span. So the beam slab member tends to the slab tends to deflect along this direction. So we need to determine the moment of inertia of the beam slab member along the shortest span of exterior panel S1. Okay. So let us see how to do that. Okay. So we need to consider the entire, width of the slab member over here. Okay. So we have here, this would be the beam, right? Here is the discontinuity. So this value would be ISP, yeah, but before that, the thickness of the slab is 180 mm. Okay, and the width of this beam section is 400. Okay, and the depth of the web is 370. Okay, and this is having a total depth of, the total width of 7500 mm. Okay, so first we need to locate the neutral axis, right? Let me write the total depth of the section over here, right? Depth of the section, that is 550. Okay, so we need to locate the neutral axis. So since we are considering the entire width of the slab member, we can expect that we can assume that it tends to lie in the flange itself rather than the web of this T section, right? So we're going to be filling up this value later on after finding out the value of x bar, right? So x bar, as usual, is given by summation of a into x bar divided by sigma a. Okay, so that would be 7. Ah, sorry about that. Let me erase and start over. Yeah. So 7500 by 180 into 90 plus 400 by 370 into 180 plus 370 by 2 divided by the total area, which is 7500 by 180 plus 400 by 370. So what is the value that we get for x bar? So the value of x bar would be 117.17 mm. 117.17 mm. Having found out the value of x bar, let us proceed to mark the location of the neutral axis. So this would be, let me take a different color once again so that there is better contrast. Okay, so 117.17, and this value would be 550 minus 117.17, that is 432.83. Okay, now we need to find out the value of ISP. How do we do that? ISP is equal to, yeah, so 7500 by 180 cube divided by 12 plus 7500 by 180 into h. What would be h? That is 117 0.17 minus 90 square plus 400 by 370 cube divided by 12 plus 400 by 370 into h square. H is, yeah, this 432.83 minus 370 by 2 whole square. Okay, that is 185 whole square. Okay, so again, I would like to remind you that this is nothing but the parallel axis theorem that is given by I ISB is equal to IXX plus A H square. Okay, so these are, two separate terms. This is for the flange part of the section, and this is for the web part of the section. Okay, so the value of ISB turns out to be, upon simplifying, how much? 15420 15420.13 into 10 to the power 6 mm power 4. Okay, let us look at the options now. So option B is the correct response. That is 15.4 into 10 to the power 9 mm power 4. Okay. Now let us proceed to the next question. Right. So this is sort of the culmination of the previous parts of this mega question. Okay. So having all the data, we need to determine the slab thickness of the exterior panel slab, exterior slab S1 for deflection control as per the Canadian code provisions. Okay, take M20 concrete and Fe415 steel, and note that the alpha BM should be lesser than or equal to 2.0. Okay, so we are having this slab panel. Okay, we are having this slab panel, and we have the floor height, that is 3.5 meter, and the column dimensions are 400 by 400 mm. Okay, and the beams are 400 by 550. We need to determine the slab thickness of the exterior slab S1. Okay, in order to ensure the compliance with the Canadian code provisions for the deflection control. Okay, so what does the Canadian code say? The overall depth of the section, right? The overall depth has to be greater than or equal to, let me write down, for better clarity, should be greater than or equal to ln into zero point 0.6 plus fy divided by 1000 divided by 30 plus 4 beta into alpha bm. Okay, so this is the Canadian code provision in order to determine the overall depth of this, two-way slab, dep depending on the various parameters. Okay, so what are these different parameters? Okay, ln is the longer clear span. Okay, so let me write down the parameters on this right hand side of the slide. Take a different color for contrast. Ln is the longer clear span. Okay, so this is the longer span, that is 7500 minus 400. Okay, that is 7500 minus 400, that is 7100 mm, right? And then we have this fy is 415 MPa, right? And what is beta? Beta is longer clear span by shorter clear span. So the longer span is it is 7100, and what is the shorter clear span? That is 5600. Okay, okay, because that is 6000 minus 400, right? So that gives us a value of 1.268. And finally, what is the value of alpha BM? Alpha BM is the average value of beta for all the beams on the edges of panel S1. So if we look into the actual alpha BM values, okay, let us go ahead and find out those values, right? So the very first value is, so it is 4.8, okay, and 2 times 2.4 and 1 time 3. So that is 4.8 plus 2 times 2.4 and 1 time 3. That is 4.8 plus 2 times 2.4 plus 3 divided by 4. Okay, so let us calculate that value, how much it turns out to be. 4.8 plus 2 times 2.4 plus 3 divided by 4. That turns out to be 3.15. So alpha BM is equal to 3.15. But there is also a clause which states that the alpha BM value should be lesser than or equal to 2.0. Okay, so we will take this alpha BM value as 2.0. Okay, so we can take finally that alpha BM is equal to 2.0, lesser than or equal to 2.0. So we'll take this value. So let us plug all the values and find out the value of D over here, or the total depth of the slab, that is 7100 multiplied by zero point 0.6 plus 0.415, right, divided by 30 plus 4 into 1.268 into 2.0. So this gives me a value of, let me just calculate, 7100 into 1.9 divided by, so that gives me a value of 179.5 mm. 179.5 mm. Okay, so we can go ahead and provide a value of D is equal to 180 mm. So this is the reason why I chose the value of D as 180 mm. So we have taken the slab thickness of 180 mm, right? So I calculated that and I selected the value of D as 180 mm so that it uh, qualifies for this for the deflection criteria as per the Canadian code. Okay, so in question 9, um, the slab thickness of the minimum slab thickness that need to be provided for exterior slab S1 is option C, 180 mm. Okay, so let us proceed to the next question. Okay, so consider the plan of this two-way floor slab, okay, that is considered in the previous question, question 9. Assuming a live load of 5 kPa and a floor finish load of 1 kPa in addition to its self weight, determine the total static moment, okay, total design static moment m naught, and the longitudinal positive and negative design moments for the interior panel S2. Okay, so this is the interior panel. Okay, and what is the value? What is the formula for the total design static moment? Okay, so the total design static moment is given by this. Okay. WU L2 ln square by 8. Okay. Okay, let me just write down that equation. Right. Okay. M naught is equal to WU L2 ln square divided by 8. Right. So what is the value of WU? Right. Let me find out that WU is equal to 1.5 factor uh, 0.18 into 25, that is the self weight, plus we have the floor finish load 1 kPa and live load of 5. 6 plus 1, sorry, 5 plus 1. So that gives me a value of WU as 15.75 kPa. 15.75 kPa. Okay, now what are the values of L2 and Ln? So L2 is the transverse span. Okay, span. Okay, that is how much? That is the span along this direction, that is 7.5 meter. And Ln is the clear longitudinal span. Okay, Ln is the clear longitudinal span, that is 6 meter minus 400, that is 5.6 meter. Okay, clear longitudinal span, that is 6.0 minus 0.4, that is 5.6 meter. Let us find out the value of m naught now, that is 15.75 multiplied by 7.5 into 5.6 square divided by 8. So this gives me a value of 463.05 kilonewton meter. This is the design static moment, or the total design static moment. Now we need to determine the longitudinal positive and the negative design moment. Okay, let us consider that this BC is the interior span. Okay, what would be the value of the positive and the negative moment? Okay, that is positive moment is 0.35 m naught, negative moment is 0.6, positive is 0.35 m naught, negative is 0.65 m naught. Let me take a different color now. So the positive moment is 162.07 kilonewton meter, and the negative moment is 300.98. So the values are 463, 162 and 300. So option B is the correct response. Okay, let us proceed to the next question now. Okay, so we are dealing with the same two-way floor slab now. So the plan, consider the plan of the two-way floor slab system given in question 10. From the total design static moment calculated, from the total design static moment calculated, okay, determine the positive design moment in the span, okay, positive design moment in the span and the negative design moment in the at the exterior and the interior support for the exterior panel S1. Okay, so essentially we are dealing with the same longitudinal distribution, so we need to focus on the panel. Okay, we need earlier we looked at the panel S2, now we need to look at the panel S1. Okay, determine the positive design moment in the span, okay, and the negative design moment at the exterior and the interior support. Okay, so we need to determine the moment at the exterior support, okay, and this is the moment at the interior support, okay, and this would be the positive moment in the span. Okay, so what are the values for that? Right, so we need to utilize these equations, right? So first we need to determine the total static moment m naught. Okay, so the total static moment, right, so that would be nothing but again wu L2 ln square divided by 8. Okay, so the data is same, for both the interior span as well as the exterior span. So the value of m naught is going to be the same, that is 436 463 463.05 kilonewton meter. And in addition to that we have the ms, right? Sorry about that. Right, so this is the equation for the ms. Okay, let me denote that using some symbols. This is ms and this is me, exterior support, and this would be mi, or the interior support. Okay, let me write down those equations. Okay, ms is 0.63 minus 0.63 minus 0.28 by q into m naught. Okay, and then we have the exterior support, or me, that is given by 0.65 m naught by q. 0.65 m naught divided by q. Then we have the moment at the interior support, that is 0.75 minus zero point 0.1 by q into m naught. 0.75 minus zero point 0.1 by q into m naught. Okay, so we are seeing this recurring term called the q. Okay, so how do we find what is the meaning of q and how do we find it out? Okay, so this q is nothing but 1 plus 1 by alpha c. And what is this alpha c? Alpha c is the ratio of sigma kc by ksp. Okay, so sigma kc is the sum of the flexural stiffness of the columns at the exterior joint, and ksp is the flexural stiffness of the slab in the along the span L1. Okay, so how do we find out those values? Let us see. Right, so let us first start by finding out the value of alpha c. Right, alpha c, mhm, is given by summation of kc by ksp. So what is the value of Kc? That is the K is equal to I by L. Okay, that is the okay. Let me simplify that. Okay, so Kc, that is 4 EIC by HC multiplied by 2 divided by 4 EISP by L. Okay, so the meaning of the term is that the summation of the column stiffness that is given by 4 EIC by HC into 2. Okay, IC refers to the column stiffness and HC is uh, the center to center height of the column. Where is that data? Okay, I think it is lost somewhere. Yeah, so this is the floor to floor height, that is 3.5. Okay, and the dimensions are 400 by 400 millimeter, right? Okay, and here 4 into E into ISP is the moment of inertia of the slab, of the beam slab section that we determined earlier, and L1 is the span along the longitudinal direction, that is 6 meter. Okay, so let us try to simplify this, and then we can proceed to calculate the value of alpha c. Okay, let me take the black color, classic. Okay, 4e and 4e gets cancelled, and this we are multiplying it by 2 because at the exterior uh, joint, two columns are meeting, right? One at the top, one that is at the top of the joint, and other column which is towards the bottom of the joint. Okay, that turns out to be, yeah, 2IC into L1 divided by ISB into HC. Yeah, so this would be what is IC? BD cube by 12, that is 400 power 4 divided by 12 multiplied by L1. L1 is 6 meter, right? 6,000 divided by ISB. What is the value of ISB? We have calculated that value. That is 15.4 into 10 to the power 9, right? 15.4 to the power 9. And what is the center to center height of the column? 3.5 meter. Okay, 3500. So simplifying that, we get the value of alpha c as 0.4743. And from this we can determine the value of q. Okay, so just try to understand the chronology. First we are going to determine the value of alpha c, that is sigma kc by ksb. From that, from this alpha c, we'll find out the value of q. Q is 1 plus 1 by alpha c. Q is 1 plus 1 by alpha c, that is 3.108. Okay, I hope it is simple and easy to follow. Simple and straightforward and easy to follow. 3.108. Okay, let us start plugging these values. Let me take a different color for better contrast as usual. That is 0.63 minus 0.28 divided by 3.108 multiplied by 463.05. This would be 0.650 divided by 3.108 into 463.05, right? Here we have 0.75 minus zero point 0.1 divided by 3.108 multiplied by 463.05. Okay, these gives me the values of 250, right? That is the span moment. The exterior support, this is 96.84, and this is 0.75 minus zero point 0.1 by Q into M naught, that is 332.4. 332.4 kilonewton. Okay, 250, 97, and 332. Yeah, so option C is the correct answer, where 250 is the span moment, 97 is the exterior support moment, and 332 is the interior support moment. Okay, we'll proceed to the next question now. Okay, so consider the plan of the two-way floor slab given in question 10, right, that we are looking at. Now, for the distribution of the moment in the transverse direction and the design of beam and slab, what are the widths of the beam and the slab to be considered for panels S1, S2, and S3? Okay, so the question is simple. We have found out the distribution of moment in the longitudinal direction along this direction, the distribution of the moment in the longitudinal direction. Now we need to distribute along the transverse direction. Okay, so what would be the width of the beam and the slabs to be considered? Okay, it is quite straightforward. Okay, so I think we can solve it here itself. Okay, so along the transverse direction, so the width of the beam would be BW plus 2DW, that is 400 plus 2 times 370, that gives me a value of 1140 mm. And what would be the width of the slab? The slab is nothing but 7500 minus 1140 divided by 2, because we are sort of dividing into three parts. Okay, I can show you actually that this is the beam and this is the slab is divided into two parts. Okay, I can actually show you in this diagram, right? So this turns out to be how much? It is 3180 mm. So what it basically means is that if this is the center line of the beam, okay, for the distribution, we are going to consider this as the beam part. Okay, this would be the beam part, right? And this would be the slab part. I'll take a different color just for better understanding. Okay, so what we are trying to say here is that the width of this beam, okay, this would be the width of the beam in the transverse direction, B beam, and this would be the width of the slab in the transverse direction. Okay, that is B slab, B slab. Okay, and the values are 1140 and 3180. Okay, so this actually, this we can actually multiply it by 2. Okay, because uh, we can distribute along this direction also, right? Or it sort of continues for the rest of this thing, and here again we have this. I hope that I've made myself a bit clear. Okay, this I need to modify this little bit. Right, so again even this part also would be considered as the slab only. Okay, and again this part would be the beam, what we are seeing here, right? This part is also considered under the slab. Okay, B slab, this would be B P. Okay, so we can actually erase this part as well. Okay, no need to divide it by 2. So this turns out to be 7500 minus 1160. The value is 3630. Sorry, 3630. So option D, that is 1140 and 3630. Um, Sorry about that. It has to be 66360. 6360. So what I mean to say is that this part, that is B beam, that is 1140 mm, and again this slab part is 6360, and again, okay, that is how we are going to distribute it. Okay, so I would like to again try to show it for you, in a more clear way, because I'm not convinced, uh, okay, let me show it here only. Okay, I'll try to explain it in a better way here. We'll take this color. Right. Here is the beam portion. Here is the slab portion, and again that is the beam portion. Okay. So let me. So beam portion we can highlight it using this red color. Okay, and then we can highlight this part also using the red color. Also beam. Okay, and then this is the slab portion. So if we were to, distribute, the slab over here, try to show this using this diagram. So this particular entity would be B beam divided by 2. Okay, this would be B slab. Again, this entity would be B beam divided by 2. Okay, so how much is that? If you add all of this, okay, the total width turns out to be B beam plus B slab, right? That is 1140 plus 6, sorry, 6360, that is nothing but 7500, which is nothing but the span along the transverse direction. Okay, so from here to here it is B beam by 2. This is B slab. This is again B beam by 2. When you add all of this, we get this equation, that is B of beam plus B of slab. Okay, that is 1140 plus 6360, that is 7.5 meters, which is nothing but the span of the slab in the transverse direction. Okay, so hence we can say that the option D is the correct response, where V beam is 1140 and B slab is 6360 mm. So the next part of the question is, for the two-way floor slab given in question 9, it is required to distribute the moments in the transverse direction. Determine the distribution of moments along the transverse direction between the beam and the slab. Okay, for the interior panel S2. Okay, so we've already determined the width of the beam and the slab. Now we need to determine the moment distribution. Okay, so how do we do the moment distribution? So we are considering the interior panel S2. Okay, the fraction of the positive moment in the spans and the negative moment at the interior column to be resisted by the beam is given by alpha b1 divided by 1 plus L2 by L1 square. Okay, what does that exactly mean? Let us look. Okay, okay, look at the, okay, what we have done here is that we have considered the distribution of the moment along the longitudinal direction, right? So in the longitudinal direction for the interior panel S2, we determine the value of the the positive and the negative moment as 162 and 301. Okay, let us build on that premise now, right? So if we consider this panel, okay, I'm going to draw the section of this, panel S2. Okay, so this is how, the distribution is, right? Consider the beam here. This is the center to center distance, that is 6 meter, right? Okay, and this was the moment distribution. Let me show you the moment distribution. We take a different color again. So the moment distribution, that is, this is equal to 0.35 m naught, and the negative moment was equal to 0.65 m naught for the interior panel, right? So now we need to determine the distribution, okay, between the beam and slab. Okay, in the earlier portion, we looked into the width of the beam and the slab for the moment distribution, right? This is the width of the beam and this is the width of the two different parts of the slab. Okay, so the fraction of the positive moment that is resisted by the beam, okay, moment resisted by the beam, or we can say moment fraction, right? Resisted by is equal to alpha b1 divided by 1 plus L2 by L1 whole square. So we know that L2 is the span in the transverse direction and L1 is the span in the longitudinal direction. So we know that, let us find out the value of alpha b1, right? So what was the value of alpha b1? Let us consider for, this panel, this b2 and b2 and c2. Okay, it is more than one. Okay, okay, so it is more than 1, so it should not be greater than 1.0, this alpha b1, right? So we'll consider that value of alpha b1 as 1.0 divided by 1 plus L2 by L1. What is the value of L2 and L1? L2 is the distance in the transverse direction, that is 7.5 meter, and L1 is the span in the longitudinal direction, that is 6 meter. Okay, 7.5 divided by 6 whole square. Okay, this gives me a value of 0.39. So what is the physical significance or the physical meaning of this is that 39% of the moment is being resisted by the beam. Okay, and the remaining 61% is resisted by the slab. Okay, so option C is the correct response. Okay, so 39% is resisted by the beam and 61% is resisted by the slab in the transverse direction. So that is what we do in the direct design method, that we determine the static moment. Okay, I'll write the brief procedure over here just as a form of recap. Okay, first is the static moment. Okay, then the longitudinal distribution of this moment, and then we have the transverse distribution of this moment. Okay, so for this particular problem I have actually done a moment distribution. For those who are interested, kindly contact me. I will just post it in the NPTEL Google Drive so that all of you can actually see the moment distribution diagram along the longitudinal as well as the transverse direction. Okay, but for this particular problem, so the correct option is option C, where 39% of the longitudinal moment is resisted by the beam, 61% is resisted by the slab. Moving on, we are going to check the slab for this one-way shear. So the distribution of the load on the two-way floor slab system is shown in the figure below. Determine the factored shear force and the design shear stress in the slab, considering the critical section at a distance of D from the face of the beam along BC, okay, along BC for the exterior panel S1. Take 20 mm cover, check for the adequacy of the reinforcement if 10 mm bars are provided at a spacing of 125 millimeter center to center. So there are two parameters that we need to calculate, right? There are three parameters. So the first parameter is to determine the factored shear force, and then the second parameter is the design shear stress in the slab. Okay, so the first we need to find out the factored shear force. Okay, so how do we do that? I think we can do it over here only. So the factored shear force VU is equal to WU into 0.5 ln minus D. Okay, so here this WU, I think I'll just copy this to the next slide and we can solve the problem over there. Okay, so what is the value of WU, right? So we can assume the value of WU as 15.75. Okay, remember that we had calculated this when we determined the total static moment for the question 10. Okay, we're going to take the value of WU as 15.75 kPa. Okay. Let me write down the value over here. WU is 15.75 kPa. Okay, and what is the value of ln? Ln is the clear span in the longitudinal direction. Okay, so the clear span we can take it as how much? 5600. Okay, please note that the center to center distance is 6 meter. So subtract 400 millimeter, that is 5.6. Okay, so the value of ln would be 5.6 meter. Okay, ln would be 5.6, right? Or yeah, 5600 mm, right? And what would be the value of D? So considering the slab thickness as 180 mm, right? So D, and it's having a cover of 20 mm, and the reinforcement is 10 mm bars, right? B is 180 minus 20 minus 10 by 2, which gives us a value of 155 mm. Let us plug all these values in this particular equation and find out the value of Vu, that is 15.75 into 0.5 into 5600 minus 155, which gives me a value of how much? 41.66 kilonewton. This is the factored shear force. Now the factored shear stress, that is tau V, is equal to Vu by V into D. Let me take a different color and solve the problem. Okay, tau V is equal to 41.66 into 10 to the power 3 divided by 1000 into 155, which gives me a value of tau V is equal to 0.269 MPa. Okay, so 42 kilonewton and 2.7 MPa. Now we need to determine whether the reinforcement provided is adequate or not. Okay, so we need to determine the value of this tau C. Okay, so we need to check if the value, if I'll take a different color once again, right? So in order to ensure that the beam is safe against shear, tau C should be greater than tau B. So how do we determine the value of tau C? Okay, in fact, it has to be tau C should be greater than K into tau V. So this K, we can determine based on this clause 40.211 of IS 456. Depending on the depth of the slab, the value of K will vary. Okay. So now let us find out the value of tau C and compare it with the value of tau V. So the tau C depends on the value of this percentage of the steel reinforcement. Okay, so we have AST is equal to pi by 4 of 10 square, which is the area of steel for 1 bar, multiplied by 1000, because we are considering unit width or the width of the slab as 1000 mm, divided by the spacing. Spacing is 125 mm, right? So the value of AST would be 628.3 mm square. 628.32 mm square. That would be the value of AST. Now what would be the percentage reinforcement? That is 100 AST by BD is equal to 100 into 628.32 divided by 1000 into 155, which gives us a value of how much? 0.405. 0.405. Okay, now because of the lack of space, I'm going to continue in this particular region. So it is given that we're using M20 concrete. Okay, and we need to interpolate between these values of 0.25 and 0.50 corresponding to this percentage steel value of 0.405. Interpolating these two values, we get the value of tau c as, so tau c lies between 0.36 and 0.48. So the value of tau c is 0.434 MPa. 0.434 MPa. So we know that the minimum value of K is 1.0. So the value of tau c, okay, okay, tau c, in fact, this it has to be K into tau c. So this K into tau c, that is 0.434, is definitely going to be greater than 0.26269. Okay, so the provided reinforcement is adequate in shear. Okay, so because K into tau c is greater than tau v, we can say that the provided reinforcement is adequate in shear. Therefore, option is the correct response. So we'll now go to the last problem for the day. Okay, so we are having this sort of an L section. We need to determine the torsional constant, for this section. Okay, let us proceed to do that. Right. We'll keep it, and I'll copy this diagram over here. Do do this to the next slide. Control V. Yeah, I think should be ready to go now. So how do we determine the torsional constant? By this particular equation. So first we need to do, what we need to do is we need to divide this into two rectangles. Okay, let me take this yellow color, right? Okay, so we can draw a separation over here. Okay, and then this square becomes, I'll take this rectangle dimensions will be 250 by so this would be 500 by 375. Okay, and this would be 250 by 250 by how much? 600 by 600 minus 375, that is 225. Okay, so first iteration we need to do like this, and the second one we can separate it like this and find out the value. Okay, that I'm going to leave it as a homework for you guys. Okay, so let us find out the value of the torsional constant. C is equal to 1 minus 0.63 into x. So x would be the smaller dimension. Okay, and y is the longer dimension. X1, and this would be y1, and here this would be x1, x2, this would be y2. 1 minus 0.63 into x, that is 375, divided by 500 into x cube y by 3, right? That is 375 cube into 500 divided by 3, plus we need to consider the other rectangle now, 1 minus 0.63 into 225 divided by 250 multiplied by x cube, that is 225 cube into 250 divided by 3. So we get the value of C as 5047.24 into 10 to the power 6 power 4. Okay. So one more iteration, one more, the second part of the question is, to divide this along this plane and find out the value of, this, find out the value of the torsional constant. Okay. So that actually we can do in this class only. Okay, let us find out, what would that value turn out to be. Okay, so in this case, it would be how much? 375 by 5250, right? So 250. Okay, and one more. This would be yeah, 600 by 375 by 250. This would be 600 by 250. So this would be x1, y1, and this would be x2 and y2, x2, y2. Okay, yeah, let me write the equation for C. Right, C is equal to 1 minus 0.63 into x 250 divided by y, that is 375, into x cube, that is 250 cube into 375 divided by 3 plus 1 minus 0.63 into 250 by 600, right, into this would be x cube is 250 cube into 600 divided by 3. Okay, now let us find out the value of this second part of the second method of dividing the L section. Okay, let us try to find out the value together. Divided by 600 multiplied by 250 cube into 600 divided by 3. So this gives me a value of 3437.5. 0.5 into 10 to the power 6 power 4. So the second way of dividing in this manner does not work. So the correct kind of a division would be is to split it in this fashion, right? Uh, yeah. So the correct kind of a division would be to split it in this fashion. Okay, and the value of C would be 5047.2 into 10 to the power 6. Okay, so we can say that option B is the correct response. So with that, we have come to the conclusion of today's session. So I'd like to just, recap, the recap of today's session. So we looked into the different types of slabs and their behavior, and then we also did the code coefficient method. We did a problem on the code coefficient method for the design of slabs, right? And then we solved the sample problem of using the code coefficient method, and then we verified the adequacy of the RC slab under one-way shear. And then in the direct design method, in the direct, we did a conceptual question on the design methodology used in the DDM and EFM. And then we also performed a sample problem on the determination of the static moment and the distribution of the moment in the longitudinal and the transverse directions as per the DDM. And then we also determined the slab thickness as per the Canadian code in order to uh, qualify for the criteria for the uh, to limit the deflections. And then in the equivalent frame method, we did the conceptual question, and then we also performed a numerical problem to determine the torsional constant of the RC beam cross section. So with that, I'd like to conclude this session. And as we know, this is the final session uh, in a series of the 12 live sessions that we have had so far. So it was a very nice experience for me. And of course, it was the second year during which I did this. And I hope that it really turned out to be helpful for all the participants who have joined and all the people who have viewed these live sessions. And I wish you all for your exams and for your careers in structural engineering as well. Okay, thank you. And if you have any doubts, feel free to reach out to me, and I'll be happy to connect and discuss any projects that you're working with and any course related content or any projects. I'll be happy to network with you. Okay, and I'd like to stay connected. Okay, thank you.